Now that we've seen how to determine the maximum solubility of a compound in solution in the last segment, in this segment we're going to look at what's called the common ion effect. In this case, we're taking advantage of the fact that we could add just one of the ions in this equilibrium into solution by pairing it with a different counterion. In this case, for instance, we're adding additional silver nitrate to this solution, and that's bringing in silver without bringing in more chromate. Now, your intuition might say, given that we know our KSP, you might recall that was a value that we were given for the last problem, and we used it to find this concentration. Now, if you were not given this concentration or this number of moles, those might be other calculations that you would need to do to start a problem like this. In this case, to speed things around, I'm giving you this number of moles and that concentration so that we can get started. So work through this problem and then unpause the video to take a look at the solution. Okay, let's take a look at how we would approach this. So our approach here, again, is going to be to use an ice table. And in particular, that's an ice table where we can leave pretty much everything in molarity. We're going to be making an approximation for this problem, given that we weren't told anything about the amount of space that this silver nitrate takes up. We're going to have to approximate that the volume has not changed. That may or may not be a good approximation. This sort of problem, by the way, is an example of why we spent time discussing molality in the previous chapter. So let's take a look at what we know to begin with. We still could potentially have this AgCrO4 column, but because it's a solid, we're confident that it's not going to be involved. We also know that the Ag plus and CrO4 2- amounts we were given are as they were when we started. So we had 1 mole of silver nitrate in 1 liter. That means that since we're talking about molarity here, this is going to be around 1 molar. Again, you might have to do a calculation to determine this molarity. We also know the concentration of our chromate because it's coming from our previous calculation. Now, what's going to be happening here? Well, this was previously saturated, and we're adding in more silver. So it should hopefully be intuitively apparent to you that if we add more silver into something that is already saturated, silver chromate is going to have to precipitate. In essence, the amount in solution can't go up, so it's going to have to go down. We're stuck together with the same stoichiometry that we had in the previous problem. That means our numbers here are going to be 6.7 times 10 to the negative 5 minus x, and 1 minus 2x. Here's where we can be, again, a little bit clever about our math. We know that the largest amount of chromate that could go away would be all of it. That is, we can't wind up with a negative equilibrium concentration of chromate. So x cannot be larger than 6.7 times 10 to the negative 5. Thus, we can be truly confident that we can neglect that minus 2x in our silver case. Remember, that's not always guaranteed to be the case, but here, subtracting 6.7 times 10 to the negative 5 is the equivalent, at most, of subtracting something that's about 3 or 4 significant figures too small. Again, this number is truly, in the mathematical sense, insignificant. So, now that we know what our equilibrium values are, let's put them into our KSP expression and solve. We're still governed by the same KSP value we were previously. We're neglecting the minus 2x, so this is going to be 1.0 squared. And we can now solve this. We can do some distributing here to find that we get to 6.7 times 10 to the negative 5. That is, that's the 1 multiplied over, minus 1.2 times 10 to the negative 12 equals x. What's that telling us here? Well, we said that this minus that was insignificant. And again, this number is so small that it's truly not significant within our degree of experimental precision. Excuse me. So, if x equals 6.7 times 10 to the negative 5, what that means down here is that all of the chromate precipitates. In essence, if you had chromium-6 in its dangerous form floating around in solution, you could add another ion to it, and it would precipitate it out of solution. Now, in this case, this x was effectively a change in molarity. However, because we were dealing with 1 liter of solution, that means that the amount we would precipitate would be that change in molarity, i.e. we would precipitate 6.7 times 10 to the negative 5 moles of silver chromate precipitated. This, by the way, is how cases with the solubility of lead pipes can be addressed. I said previously that lead is more soluble when more chloride ions are present, but by comparison, sulfate is much less soluble with lead. So by adding in a modest amount of sulfate to drinking water, lead pipes can be rendered once again insoluble and a community safe. So the common ion effect is more than a quirk of the mathematics. It's also a tool to solve meaningful problems.